what will make a definition of a wave. There are different elements. Is frequency. We put in hertz. So 1 hertz equal 1 wave per second. That's just a definition. And there is the length of wave. What is the length of wave? How to express that very easily and clearly? Yeah, let's stay in the air. Okay. The sound waves in the air propagate for 340 meters. I don't know what this is in miles or inches or things. You probably have the formula in euro scales, but okay, it's 340 meters per second. So it means that a wave that has a frequency of 340 hertz is 1 meter long. For the same frequencies in different environment, it would be a different length. But in the air, it's actually by time it's just 10340. That's a portion of the length of wave of a wave of a certain frequency. So if it's 340 hertz, divided by 340 is 1. And the other element is the amplitude. Okay, what is the amplitude? Is the force you put in it, and we'll see the way waves are developing and what amplitude means. So I will take to show those things the simple wave that exists. It's a pendulum. Okay, a pendulum is a way that it's hanging on a wire, and we have to put that in motion. What we do to put that in motion? Okay, you say move. To move it, we exert a force on it. So force, energy. I put a force on it and make it move. As it hangs to this wire, it's going to follow a circle. The more energy I put, the higher it's going to come. The less energy I put, the lower it's going to come. So this initial energy will give the amplitude. Actually, the amplitude is this length. Okay. So we join the point A. And it stops there because it doesn't have energy enough to go further. What happens while A stops there? My weight stopping in point A.
Gravity wins over?
Yeah, and goes down.
Goes down.
Okay, so he started in O, I say O for origin, went to A, but that's one movement. From A goes back to O, and then after that, other way, okay. Till here, let's say here, to point B. And then?
Goes to point C.
Okay. Oh, and then?
Back.
Where?
To the right again, or well, you're left.
Yeah, but till what point?
Could be C.
Halfway. Halfway.
One B here, why? Interesting. Is losing energy, is losing amplitude, so it will reduce the distance, indeed, and will come to, let's say here, we'll name it A prime, Then from there goes back to B prime. We notice that I put B already a little lower than A, etc. A second, B second. To stop back on 0. Okay, what is a wave in that? A wave is a movement. A wave is the movement of this. How shall we name it? Weight? I don't know. Okay, let's name it O. Okay. My man O. Moves. Till here. So, one wave is the movement O, A, O, B, back to O. From O to O doing all this trip, that's one wave. In this wave, the amplitude is the distance OA. We see that in the process, it's going down. The amplitude is diminishing together with diminution of the energy. If the energy goes down, the amplitude goes down. You want to have a bigger amplitude in your sound, put more energy. You want it less energy. That's right in proportion. So now the frequency. What makes the frequency? One observation that's pretty interesting with this. Let's take all this away so it's clear. So one rare thing we observe with the movement of the pendulum, and that's also the real definition of the wave, is that while we approach it with the time needed for this to go from O to A is exactly the same that it needs to go from A to O, and the same time it needs to go from O to B. And at the same time, it needs to go back to C. At the same time, it needs to go back to A prime. So what happens? You can imagine that if the energy goes down, the speed is slower, which is true, but the distance being smaller, the total time to make the different distances is exactly the same. So that's one constant, is the frequency. Actually, the frequency is the time it needs to complete one movement OA, OB, O. Could be prime, second, whatever. You know, that will just depend on the energy. So of course the movement of the pendulum itself slows down, but the total distance it makes takes the same time in proportion. Actually, if you analyze it a little more, you have an acceleration while you put the energy, then it decelerates to stop there. And then to reverse its direction of movement, accelerate the maximum here, decelerate, and same process. So the speed of the movement is absolutely not constant. There's variations on all the trip. But the total time for the different distances are always exactly the same. What will influence the frequency in this case? No, we've seen we put more force, we make this distance bigger with the same time. Indeed, which can be compared as the length of wave. That is actually the length of wave. If I put it here, I make it longer. So longer wave. What will happen? I put the energy in there.
Take longer to make your trip.
Indeed. So we'll slow down the frequency, as we've seen here in the comparison. If we have a longer wavelength, it's a lower frequency in the same environment, in same conditions. Okay. So on the opposite, if we want to have a shorter wave and a higher frequency, we shorten the string. Okay, I think that's very clear for everybody, and you would have looked at me like, whoa, what is that? I don't know all the time how fast I can go with those things, but it's okay. So now we had a simple wave, but we were talking about a complex wave. So we try to apply that. I use always this image because it's the easier way to do it. Here we have a string with those 2 points. And what we do with the string, like on a guitar or whatever string instrument, we put the string in movement. How we do it, we pinch the string and we bring it here. Actually, it's not that. It's not. O prime is C and C prime. Okay. So we take the point that would be here, O on the string, and we bring it there to A. What happens? This goes back to O and goes to B. And then from B goes back to O, goes to A prime. So we have that. And same thing. But it's not only what it is doing. You can visualize that pretty good on a string instrument, even on a guitar if you concentrate on the bass string. Actually, it vibrates on itself too, the string. It's kind of more understandable because there is nothing to handle it. If I pinch the string here, what will happen? It will also separate. You can really visualize that on the string guitar. If you have a good spotlight on the bass frequency, you do that and you see all those movements. And actually, you have a division here. And it's really like the cut of the diamond. It's based also on harmonics. Well, I like this figure. You know, actually each part of the string vibrates like it's its proper string, and the whole string vibrates, so the whole movement is kind of crazy, unbelievable, very complex pattern of overtones. So note that's an observation that was already made by the ancient Greeks that really concentrate on the mono string, monochord, as they said. Made all study of sounds and scale was actually developed at that time, was by observing all the physics of the string. And it happens that it vibrates on just entire multiples. So you have the main wave is the total length, is one, then the second wave starts here. It's just the double of the frequency because it's the half length. So that's the sound 1. Sound 2 is the double of the frequency. Then the third, 3 times the frequency. The fourth, 5, 6, 7, 8, 9, 10, 11, 12. Okay, I stopped to 12 because we consider that the saxophone develops 12 harmonics. It's a consideration. It could be way more. There are no limits. There's one thing that you have to know. You can always divide a vibrant element in smaller sections. So the limit to play in the high range is not any instrument. It's only the approach of getting those harmonics out of the instrument. So to develop the limits on the high range, the limit is you, not the instrument. To develop it on the low note, the limit is the length of the vibrating element. So in the case of the saxophone, it's hair. We will transpose that to hair. But I was showing on the string because it's easier to visualize. So the limit is the length of the string. Of course, there is one element that's the tension too. If you reduce the tension of the string, you will lower the pitch. It's the same with the hair. If you reduce the pressure of the hair, you will lower the pitch. Okay, so now we can analyze it a little more. Let's consider that this would be a C. And that's, I would say, really theoretical. What would be the sound 2? It's a double of the frequency. Octave. That's the definition of the octave, actually. It's really theoretical. It's the double of the frequency. So it's C2. What would be 3? Is the triple of the frequency, and it is. It's a G, yeah, which is 1 octave and a quint above the fundamental, the lower C. So 4, it's twice to C3. The 5 is 5 times the frequency and is a major third above this. What is 6 is the double of 3. Is a G, is a minor third. What we observe, the higher we go, the smaller the interval comes. So what is the sound 7? Close to B flat indeed. 8, the double of the double of the double, C4. 9, yeah, let's say it's a major second, D. 10, it's a double of 5 is E. So then it's a minor second, it's getting smaller and smaller. 11. It's in between F and F sharp. It's hard to say it would be an in-tune note. And the 12, again, a G. That would be pretty constant. So the quint and the octave are pretty constant in this development. But the notes in between, more hazardous. Okay. As soon as you stay till this, till 8, let's say it's okay. Then up there, it's a little more hazardous. So that's the development of the harmonics. That's one part of this complex combination. What will make a sound signature, I would say. What's the word in English? You say timbre? The timbre, yeah, more than signature, because the timbre would be defined by the relative amplitude of each of those harmonics. If you have a lot of quint, it's going to sound warm and mellow. If you have no quint, you will have more of the lower harmonics, but you'll hear the higher harmonics more, so it will sound a little sharper. So that will give the color. There are other elements to really develop a sound signature, I would say. I think that's very clear for everybody else. So, okay.